Welcome back. It's lecture number 7. We get to talk about data today because, after all, this is a data science class, right? So I guess we should speak at least a little bit about what data is, what is it not, what can we do with it, what does it look like when we get a hold of it, how does the forms we get a hold of it affect how we process it. And we also get to play a little bit about just showing off some cool data analysis. So let's get to it. Do want to start by just reminding everybody that the first reading is due tonight, the quiz. It started on Thursday. It's going through Friday. So please finish it off if you have not already. Reading number 2 is already available on Canvas. So feel free to get after it. It's a lot shorter. And this one's, well, I'll just let you read it and think about it, because this is definitely something I would encourage you to think about what you agree and disagree with in reading number 2. And then the quiz on that will be next week, and we're going to keep it in the same time slot. I'm just going to shift it over so that the quiz is always available Thursday and Friday. All right? Now, let's start off by doing a short little quiz right here. So I just want to find out whether people have really kind of grasped some of the topics we've talked about so far during the quarter. So just take a look at these, answer them, and let's see how you're getting on with the things we're talking about. All right. So this is the other one, but you'll be able to do that on the Google form. So, like I said, today's topic is data and data types. What are they? How do we understand how data is available? Let's take a look. Objectives. Well, we want you to be able to understand what a variable type is, what kinds of variables can be encoded in data sets we can work with. I also want you to be able to understand the differences between ways in which data is stored commonly. There are more data formats than you can possibly shake a stick at, but there are some very common formats, and especially very common formats in the data science world, so we're going to talk about those. And one of those common formats is a relational database. This is not a course in databases, so we cannot really get into it except to give you a flavor of what database operations are, because while most people have encountered a spreadsheet some point in their lives and they understand tabular data because they have already experienced that kind of data, very few people who haven't taken a bunch of computer science have ever seen a relational database before. And so we're going to get a little bit more into the nitty-gritty of that kind of thing. So nitty-gritty, well, let's jump right in. What is data? Yeah, there's a very simple, obvious answer. If you can store it on a computer, it's probably data. That is not to say that actually everything that is data is stored on computers. Okay, that is a category error. All right, things can be data but not happen to be on computers yet, or will never be on computers. But they can, if it can be stored on a computer, then it's a clear indication that it's data. Okay, so all these things, crazy numbers of things out there in the world, are data. Everything you've ever posted on a social media site, every website you've ever visited, or file you've streamed off of Spotify or YouTube Music, everything you've got in your hard drive, a list of things that you happen to have on a piece of paper but that could go onto a computer, all of your homeworks, everything. So basically, if you can enter it into a spreadsheet or take a picture of it, write about it, make a video of it, record it on audio, encode it into language or numbers, then it's data. Okay? it is also relevant to ask what is not data. I'm going to let you stew with that for a second before I go to the next bullet point. What do you think is not data? Well, for a starter, any subjective experience you have, like an emotion or a memory, a feeling, also anything that's out in the real world, like continents, mountains, trees, insects, Bambi the deer. I mean, these are not data. But on the other hand, if someone measures these things, then that is data. But the actual subjective experience you have is not data. Whoops, we missed a very important thing there. So measurements are not the thing. They're not the process or idea that they measure. That's really what I wanted to get at. They are, in fact, not the same thing as what they're measuring. Measurements are data, but measurements are not the thing. And that is one of the key takeaways that I would love it if you, like 3 years from now, working as a data scientist, if this is the kind of thing that you are always thinking about. Because a lot of people make mistakes in analysis by assuming that the measurement they have is the truth, is the same thing they are measuring, or the same thing they're interested in measuring. And they are not the same. And it's important to keep that into your mind as you're working. All right, so how do we store data? What do we store? Well, we're going to store information in a variable. Variables are the same thing as saying a feature. And you might hear these words used interchangeably, variables or features. Machine learning tends to use the word feature a lot. Normal everyday people who maybe have had algebra and haven't gone a lot further in their mathematics might use variable. But we mean the same thing. We mean a measurement, but our measurement of Bob's height is a particular measurement, but height is the variable. Okay? Variables come in different types. Quantitative variables are quantities, they are numbers. Okay? So if something is a number, represented as a number, then it is a quantitative variable. They could be integers, counting numbers. How many people at this party? 12. Okay? They can be continuous numbers like Bob's height, okay? Which could be 5 foot 10 and a half inches, right? Or it could be 65.84 centimeters, right? Qualitative data is got a quality to it. It is not numeric. So the quality is the word that you're writing, a string. Or it could be that it belongs to a particular category, right? Like we have data about whether or not a show is good or bad. Does it belong to the good category or the bad category? So let's take a moment and give you a chance to show that you understand all this. So I've measured your height and entered it into a spreadsheet. It's 68.2 centimeters. What type of variable is this? Likewise, you will have just answered on the Google form this one. So we can categorize data storage by how structured the storage is. Some things are highly, highly structured, like relational databases. They constrain the way knowledge is represented so you can easily find knowledge. That is the whole point of a database, is because it makes it easy for you to find the numbers you need because there is a relationship among the way variables are stored. Unstructured stuff is photos of your kids and family. It is the audio on your computer, and so on and so forth. It doesn't have strong relational links, and it doesn't even have some little markups to help you do stuff. although actually the audio may. And actually even now that I think about it, images do too, right? These things often have metadata embedded in them. They have something that might make them a little bit more like semi-structured data, which I'll talk about right now. Semi-structured data is data which helps put something into the way the data is stored to help you understand what it is. Okay? So if you've got a spreadsheet, right, it makes everything into tables. And tables help you understand what the numbers mean, that this is the variable that's named at the top of the column, its height. Height variable at the top of the column, and the stuff underneath it. Okay? While the video and audio files that I was talking about before aren't as structured as a spreadsheet table, they do contain metadata, which gives information about what the song is, how many plays it's had, whether or not it's got a fast beat or a slow beat. Those kinds of things are encoded in the metadata, not just the actual waveforms that you hear. All right. So semi-structured data is in many ways the thing that data scientists use the most. So the most common file interchange format in the history of data science is the CSV, comma-separated values. Comma-separated value files are simply line by line. Each row is separated by a new line, and the columns are made by where a comma is. So each column is separated by a comma. Pretty easy to understand as a human being, very generic to exchange between computers. They have their problems. They have a lot of problems, actually. You can have a lot of nightmares dealing with CSVs, but they are fundamentally incredibly common because every piece of software and computer out there can operate on them. And really, a CSV is not any different in structure than some more complicated tabular data formats like a spreadsheet. Okay? And in fact, you can usually, every spreadsheet like Google here or your Microsoft thingy are all going to be able to import and export CSV files as well as their native file format. And exchanging information in an Excel file is not very different than exchanging it in a CSV file. All right. So a very different way to have semi-structured data is a JSON file. And JSON, I just enunciated it so you can see it. Nobody calls it that. It is called either a JSON or a JSON file. As a JSON, I highly encourage you to call it a JSON file. It's an acronym for JavaScript Object Notation. And it's a way in which you can both easily read the data, like the CSV enabled you to do, right? So humans can read it, and machines can read it. And that's very easy for both humans and machines to make these files or to read them. So it's a great way to structure data. It's structured very, very differently than a CSV file. A CSV file and a spreadsheet are both tables. Fundamentally, they're a table. This is a key value setup. So you have a key like name, that's the name of the variable, and then a value, Isabella. All right, and you can structure data using this format. So here's a little bit more of a JSON file. So we might have something like an attributes key. Okay, so this is attached to a restaurant. Okay, so maybe this is Yelp. This is the way Yelp is storing their data. And every restaurant in Yelp has an attributes thing attached to it. And the attributes are, does it have takeout? Does it have Wi-Fi? Does it have a drive-through? Okay? Another attribute is, what is it good for, this restaurant? Well, it could be good for any one of these categories. This restaurant is not good for any of them. Okay? And every single restaurant's data in Yelp is going to have an attributes thing attached to it. So this is the way in which we can look up these things, right? So when we make a query to Yelp and I ask for Underbelly, which is a ramen restaurant near me, okay, then I can get the attributes from Underbelly and find out whether it's got takeaway or Wi-Fi or any of that. So now, a similar concept to a JSON file, and in fact an older version of this same kind of data, is when somebody uses a markup language. A markup language, rather like a JSON file, puts structure into the text itself. Okay? The markup language you maybe have seen the most but never noticed is HTML, hypertext markup language, which is what a web page is built out of. And every web page you've ever surfed is written in HTML. And the structure of all these markup languages is the same. There's some sort of content, and the content is surrounded by tags. And tags have two things. They have an opening, and they have a closing. Okay? So here we have a tag, and that tag is good for everything inside here. It says it tags every bit of text that's between here and the closing. Okay, so these two go together. Everything enclosed by those tags is one unit of information. But they enable nesting, just like the JSON file did. Actually, I forgot to call that out. The JSON file had that nested, what is it good for, which is inside the attributes. Okay? You can do the same thing here. Inside tag is tag 2, right? And also tag 3. It's also important to note in most markup languages that white space and line breaks don't mean much at all. So you can have this thing where the tag 2 is actually the closing tag looks like this, right? But you can break it up across lines the way you see it here. Okay, so markup languages are terribly common out there. Like I said, things you may encounter, HTML. If you write a lot of mathematics, you may use a markup language called LaTeX. I certainly having my students in my machine learning course that I'm also teaching right now are using a lot of LaTeX. So you'll see this kind of thing. Okay, so unstructured data is just raw data without any notation on it to help you understand what it means. Semi-structured data is maybe something like free-form text with markup tags in it, or something like a JSON file or a CSV file where the text is surrounded by elements that help you interpret it. Okay? But really well-structured data is in a relational database. So in relational databases, you will see that there's a bunch of tables, and those tables are linked by unique identifiers. They provide a really easy way to store data efficiently to make sure that when you do operations on it, there's no ambiguity, like there's no way in which you could accidentally have a different interpretation of a query than when you try to make something happen. They can also increase privacy. They also have excellent properties for when loads and loads of people all want to access the same data. That's a good point at which relational databases excel. So relational databases you may mostly see are going to be called SQL or SQL. Most people will probably say SQL, but some will say the initialism SQL. Okay. So how is it structured? Information is stored across many different tables. And like I said, there's a unique identifier which you can see across tables to help get the information from many different tables and unify it together into one query. So how does that look? Let's say we've got our Yelp restaurant data, okay? And there are 3 different tables we're looking at. A table which has the restaurant, its address, and its kind. There's another table which has health inspection reports, and a third table that has the, overall rating of the restaurant. So when we want to find anything related to a particular restaurant, we can find that by using that ID and querying across those tables to get the information we want from each one of those tables and then match it up to get the answer to our question. Okay, another thing about unique IDs is that they are unique. So it's not always the case that things you might think of as identifying, like an address or the name of a restaurant, are always unique. There can be multiple restaurants at the same address. There can be multiple restaurants, Roberto's, I'm looking at you, Roberto's, that have the same name. By the way, if you're interested, so San Diego longtime people, you will know that Roberto's is a local thing. There are about 20 burrito taco places called Roberto's. They are similar but non-identical. They are owned by a wide variety of people. And there was a really great article actually in the local newspaper just recently about why that is, because it is basically a big family that originally owned it, and then it broke up into lots of little competing sub things because family stuff. And the matriarch of the clan recently died, and her obituary is like really kind of gets into what all that stuff was. But at any rate, little bit of San Diego lore. And if you're asking me, the best Roberto's is the Roberto's on Claremont Drive. So we can use unique IDs because they're unique to positively identify the restaurant that we are talking about, whereas other kinds of tags may not be unique. Okay, let's take a look at how SQL stuff works by continuing on with our food theme. If anybody's not familiar with the Great British Bake Off, it is a TV show that makes you hungry. The baking competition it's so British, it's incredible. So if you're an Anglophile or a baking fanatic, you almost certainly already know this. It is filmed in a way which is probably familiar to you if you've watched any kind of cooking challenge show. Each contestant has to do several different things. First, they have a signature challenge where they get to show off their tried and true recipes. There's a technical challenge where they're asked to undertake something for the first time with minimal instruction. And then there's like the big, huge showmanship kind of competition. So what kind of data would a show like this generate? Well, let's take a look and see what's out there. We might have a table which is organized to show you how each episode, how popular it is, right? So we'd have the series and the episode and the date at which it hit and how many viewers it had in measurements over a week or over a month. Okay? We might have more data which demonstrates which each baker is and whether they continued on because it's a challenge and the winner stays kind of thing, right? They also might have data which is organized to show you information about the US season as opposed to the UK season because, of course, it came over here much later than it was originally airing in the UK. We might have information about what each baker was doing. So what their signature move was, what they did when they were asked to pull out all the stops, what their quantitative rating was, and when they went through the technical challenge. So, we might also get more information about the bakers, like how old they are, where do they come from, things about each episode, about who the winner was in a given episode and who the runners-up were. Okay? So let's imagine we're going to do some operations now. We have these different tables: results, challenges, bakers, episodes, and series. And we want to look across these things to see what's common when we want to grab data. Well, series runs all the way through all the tables, as does episode, except for on the baker table, because bakers can appear in multiple series, right? So as they go on and on with the challenges and make it to the next time. So there was no natural episode thing here. Okay? So what if we want to do some stuff with this data? What if we say wanted information about all of the challenges that had been done, right? So here we have information about what was baked, right? These are the challenges information. But we don't know anything about, in this table, the result, about whether the person who baked something went on to win or not. Over here we have information about the result in a given episode. Well, what if we want to combine these two and figure out what kind of challenges were winners? Well, to do that, we have these two data sets, right? We have the challenges, which has series, episode, baker, what they made. And over here we have the results in a separate table where we have whether that person was a winner or whether they got eliminated. Okay? So we want to combine these two. We want to find, for instance, any time we have information about both. So we want to join information from the challenges table to the results table. And what we want to do is we want to grab everything where we have information from both tables. Okay? Because we only want data which is complete, where we have all the information. So here we have Anitha and Ed in episode 6 and episode 1. Okay? So we want to join those two together. And we're going to create a new table which has only those two entries, those two rows, but it has all of the columns from both of the tables. And that is called an inner join. An inner join is when we take all the rows that we have from both the tables that we are joining together. Okay. Once again, just to remind you, these are SQL relational databases, and this is how they work. They work by joins. The join is the fundamental operation in a SQL dataset. Well, we could do something different. We could join everything in table number 2 in the results that we had information about in table 1. Okay, this is called a left join, where we take the first table and we join things in this table onto it. Okay? So a left join includes all the rows in the first table. Everything that's in that first table is here in the left join. But there is missing information on the right table. The right table didn't include any information about Ruth and Holly. Their entries are not here at all. So we have missing information. Okay? Missing information can also be called not available, and that's where NA comes from, right? Missing information, we can fill it in with we don't knows, not available. There is a very related abbreviation which you will see over and over again in computer science, and that is so when there's some data there, but it's not interpretable as a number, right? So things like infinity, which is not a number, get represented sometimes this way, or divide by 0. But also times when you try to interpret something that is inherently a string as a number because you accidentally did a bad operation, which you shouldn't have done. You shouldn't have tried to use a string as a number. Then you may get that. But I just wanted to point that out, not because it's here, but just because you may encounter the terminology that not available, NA, is not the same thing as not a number, NaN. Okay? They are not the same. Sometimes you will see a null for something that is both, right? Nulls just mean we don't have a good value here. And nulls could be for it's not available, or it could be for a not a number. Either one can be a null. Okay, so I should, I guess, notate that while we're getting into the nitty-gritty details. Okay, but really, that's not what we're talking about here. I just wanted to show you things that people get confused about. So, if you have missing information, when you're doing a left join, when that information's not in the right table, then it comes out as a not available, as an NA. All right. You can do the right join. So you're going to include every single row in the right table and pull the left table into this. But if missing information exists, like there's nothing about Ben here, Ben doesn't exist in this table, then we can do a right join, and Ben's information from table 1, from the left table, is NAs. Okay? So inner join, get everything that's in both. Left join, get everything that's in the left and fill in missing information with NAs. Right join, get everything that's on the right and fill in missing information with as NAs. And the full join is everything, everything, everything. Okay? So you get NAs on both the left side and the right side. And it's just essentially a full join is just smashing the two tables together. Okay? So it's the least useful thing in many ways. Okay? So once again, if we look at it as a set notation, an inner join is include any row that's in both tables. And it does it by those unique identifiers, whatever you specify as the unique identifier. The full join is any row in either table. Or we can do it this way, left join and right join. Okay? Well, let's do a little quick review. Say we have 2 tables. Actually, 3 tables. My bad. Sorry. Man, I need more coffee. All right, you couldn't even see me take that coffee because I had this off for a long, long time. All right, here we are. We have some tables, and I really, really hope you've watched Stranger Things because, man, oh man, was that a happiness-making show for me. So all these characters that are in this show and their qualities are in these 2 tables, and we want to go ahead and take these 2 tables and combine them to make this table. What's going on here? Which join is doing this? We're joining these 2 tables to make this table on the right. So which join operation is making this table? I will give you a moment to answer. And And there is a second one that we want to ask the same question on. You will have done that together in the same Google form. All right. So you've had a chance to show that you understand what we were talking about. Let's talk about unstructured data because it's so common. It's everywhere. Most data is unstructured. Although actually I disagree with the inclusion of social media here, because social media data, when you operate on it, is usually in a JSON format, which is semi-structured. So guess I should have changed the slide instead of just using it. And as I said, many files like audio files and video files will have metadata, which enables you potentially to get some sort of structure into it, right? Like if your camera, like say your phone, has a GPS in it, it will location stamp every photo you take. And if you upload that photo, that's how iPhoto or Google Photos or whatever you're using knows to organize your photos by location and let you browse all the photos you took at your favorite restaurant. Okay? So many of these things are potentially semi-structured, but in other ways they are unstructured, or they can be operated on as unstructured. So text is the original unstructured data set. There is so much text out there, Wikipedia and all the books that Google have scanned, but not much of that has been gone through and annotated so that it has a structure to it. So what we can do is we can do analyses of this data with in spite of the fact that it's unstructured. It just takes more effort. So one of the ways that people deal with that is to make the analysis relatively simple. Rather than, say, understanding all the parts of speech and the exact meaning of a sentence, which can be very, very difficult and is only now becoming something that's semi-reliable, we can just make a much easier analysis where we try to judge, is a given piece of text happy or sad or neutral in its outlook? So by recasting the problem easier, we can get enough labeled data to make a good sentiment analyzer, something which says a piece of text is happy or sad or neutral. So we can take all this huge amount of data out there and we can take a look at it. Okay? So somebody somewhere has made a sentiment analyzer, and we're not going to get too into the details, but let's just say it's relatively good at counting up happiness versus negativity. And we have all of the text of Jane Austen's novels because she's old and stuff, and so all that text is in the public domain and easy to grab a hold of. And we can look at how the sentiment of a book changes over time. So Jane Austen generally wrote about fairly fluffy, happy things. There were certainly negative moments, but they were relatively brief compared to a lot of parties. So we can see that the vast majority of Jane Austen's sentiment is in the positive side, in the happy side. And along this axis is the unfolding of the book. If you will, each one of these data points is a section of text in the book, with the beginning of the book over here and the end of the book over here. So this is Sense and Sensibility, this is Pride and Prejudice, this is Emma, and so these are all famous English novels, if you've never read them, from the 19th century. And things mostly go along happy, and then sometimes they get a little dramatic and sad, and then they get happy again. And you can see that, Mansfield Park, which has kind of a downer for the most part at the end, is a very unusual book for Jane Austen. Okay, so this is just one way in which we can take unstructured data and operate on it, because we do the analysis in a way which is so restricted that we can work with the data even though it's highly unstructured. Another very common text analysis, and again, most text is unstructured, is web scraping. Web scraping is totally a data science thing. Lots and lots of information is out there on people's web pages. And while it may be out there on their web pages, they may not make it freely and easily available to you except through a web browser. Well, that's no limit. You can use a program to pretend to be a web browser and grab that data. And then that data has to be parsed. It has to be pulled apart into pieces in ways which enable you to use that data. And there are all kinds of ways to do this. In the world I work in, Python, the gold standard tool is called Beautiful Soup because everybody loves a dumb name. So Beautiful Soup is a web scraping library which enables you to very quickly and easily pull parts of a web page apart and turn it into semi-structured data. Okay? So what this article did, which you can find right here, is it took a New York Times article about President Trump's tweets. And the New York Times article was throwing out a bunch of tweets in the first several days of his presidency, and it went through them and rated them for falsehood or not. Okay? So this was all in 2017, right after he came into office. And so this is what the article looks like on the New York Times website. It has a tweet, it has the date that the tweet happened, and it has a sentence saying whether it was a truth or a falsehood. And if it was a falsehood, why? And the falsehood also will have a link to some information demonstrating why this was a lie. Okay? So this is the article on the Times website. Somebody else wanted to do this kind of analysis themselves, but they didn't have access to the New York Times' data. They didn't make it freely available. Trump's tweets are freely available, but Trump's tweets don't have attached to them the falsehood rating and the falsehood link about why anything was given falsehood. So this person wanted to maybe redo this analysis or maybe do a different thing with the same data. So if you want to do that kind of thing, you can web scrape. Okay? And so this, just demonstrates the kinds of nature of different kinds of analyses you can do when you have the data. You can look through it for everything about China, okay, and currency manipulation. And you can just go bang, 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 and do an analysis once you have this data that you've web scraped. Okay? So when we're doing this web scraping, how does this work? Just to give you a flavor of web scraping in general. Okay? You can think of each lie as a record. Okay? When you look at the HTML, the code in the website for a given chunk of the New York Times article, you can see that there are markup tags. Okay? The markup tags contain the information that you can use to grab a hold of the data and make it structured. So the HTML has this strong thing, and that strong is what generates the red here, okay? So this strong around the date is a good way to grab a hold of the date information and stick it in the slot in your program, which is for storing date data, okay? Then there's the tweet, and then there is this span called short truth, and inside that short truth thing is the explanation of why it was not true, and inside the tag, the web address, which shows the supporting information for why that's a lie. Okay, so seeing that this is how the code that generates the web page is structured, we can see there's enough structure in the web page to grab a hold of things we're interested in, pull them out, and reuse them. So again, just a recap of what I said. The tweet information comes in terms of date surrounded by strong, the lie, and then this short truth tag, which contains the explanation and the link. So we can use those structures to grab a hold of this data and transform it. So this is a short bit of Python code where we I should say, I know you guys haven't had any programming. I understand that. This is not something you're going to be tested on or have to know. This is a way to show you what data scientists do, right? And if you happen to have enough Python to understand this code, then great. That's awesome. And if you don't, just let it give you a flavor of what it looks like to do this kind of work, okay? So we're going to loop over everything that comes off the web page. And we're going to try to look for that strong tag. And we know that it's going to be some text. And we're going to parse that date out because that date just said January 21st. It didn't say a year. We're going to add the year to it, okay? And we can do that for each element that we were talking about, where we showed that there is structure in the HTML which lets us find the data and scrape the data off. So then we can create a long list of all of this data and turn it into a Python data structure. And when we have this Python data structure, we have a list, and in that list is everything we were interested in: the date, the tweet, the explanation, and the link. And then we've got the next tweet down here, and so on and so forth. And now this is on our computer, and we can operate on it, and we can do the analysis. Okay, we've grabbed the data, we've grabbed it with structure so that we can actually do anything we want to in terms of an analysis. At this point, I would definitely turn it into a data frame, and a data frame is just a nice way to handle data as compared to a list of things, which is what we had before. A data frame is rather like a spreadsheet, but even better. So I will say that if you continue to do data science in Python, you will definitely use these kinds of pandas data frames. They are phenomenal because they let you operate on data in many different ways, and they're great for handling data, finding missing data, taking care of missing data, all that kind of stuff. Plotting, it's all in here. All right. Stop, back up. Let's talk about a different kind of unstructured data, okay? We can talk about the data that you might find in images. So Google Maps has all this Street View stuff, and it's very interesting. It turns out that this data can be used to predict people's voting. Well, if you train, you have so much data here. There are 50 million images in Street View at least. This was many years ago, so there's a lot more now. There's voting records out there. We can make an algorithm that detects cars and classifies them based on make, model, that kind of thing. And then once we've done that, we can look at correlations between the cars that are seen on a neighborhood streets and its voting record. And if we put those two together, we can make a prediction on data that we've never trained on, which in a given neighborhood, we have a bunch of cars. Those cars are more correlated with a blue vote or a red vote. How does that look? So what you can see from this paper is that this is the actual voting record for a county. And once this algorithm has been trained for a bit, it's learned to correlate cars and votes. We find out that it can indeed reproduce the voting pattern of a county reasonably well, neighborhood by neighborhood. And all of this is just based upon vehicles that are in the images. Some little machine learning magic I don't have the knowledge or time to go into, which can pick out whether something is a pickup truck or a sedan. And I grew up in a place with an awful lot of pickup trucks, and I now live in a place with very few. So, little quick question to you. Do you think that this approach that was trained on one election would work on a very different one? All right. Because of time, I want to kind of skip this bit here, except to note that we can do similar operations on text. As we've done on text, we can do it on audio files. Okay, but I want to kind of stick with the text because it's easier to understand, and I already apparently blabbled on too long. We can ask all kinds of information about lyrics. Okay, and if we wanted to know more about repetitiveness in pop lyrics, what kind of data would we use to answer the question? Quick quiz. One I unfortunately gave away the answer to when I was running the intro. All right, so we can look at several things. We can look at the number of unique words in a song, but that metric would quantify these two songs as equally repetitive. They have the same number of unique words, but they yet feel very, very different when you look at them, right? Because this one is repetitive. I love cheap thrills, right? So it clearly has a repeat. But yet this one doesn't have a phrase repeat, but it has the same number of unique words. So we could, for instance, use a different way to look at this than a unique word count. So you may be familiar with lempel-ziv because every time you've made a zip file, that zip file is a lempel-ziv compressed thing. And what it looks for is it looks for structured repeats. And if it finds a structured repeat somewhere in the data, then it just says, okay, this structured repeat is element number 65. And instead of writing the thing twice or 5 times, it just writes a 65, 65, a 65. And it replaces every unit that can be repeatable with an index and just says, here's another one of these. Okay? So if you run a song lyric text file through a zip, right? You just compress it with whatever tool you use on your desktop to make zip files. You can find out how repetitive the song is by this metric. So a song which goes from, say, 300 kilobytes down to 3 kilobytes is highly repetitive, whereas a song that goes from 300 kilobytes of lyrics down to 120 is less repetitive. So the world's most repetitive song is Around the World by Daft Punk. Okay? And as somebody who actually liked early Daft Punk and now thinks they're pretty trash, I endorse this. Okay? Things like an essay don't contain a lot of repeats. But songs have a distribution. Some of them are highly repetitive and get reduced in size quite a lot, and some of them don't get reduced well at all. They're quite unique. It's interesting, you can look at repetitiveness over year, and more recent years, you're seeing more compression and therefore songs are getting more repetitive. But it's always the case that the most popular songs are more repetitive than the average song. So, but we did mention vocabulary size, and I want to take a moment to go after, go after that question. So we looked at compressibility as a measure of text, and we can do interesting analysis with that, right? Even though the data is not structured in any way, we can still find out interesting things about song lyrics. But this is like maybe my favorite thing on the internet. So I have to show it to you. Let me get over there. All right. So hip hop has very different kinds of strands running through it. Some of the hip hop strands love language, and they play with language in ways which are surprising and unique, and those artists tend to use a lot of vocabulary. They have great, huge reach of words. But, remember what we saw with the compressibility thing, right? So you can have something which is actually repetitive, but doesn't have a large, unique vocabulary. So this is a different kind of metric, all right? So if we look at an artist's first 35,000 lyrics, right? So that just allows you to take an artist who's relatively early in their career and hasn't had a gazillion songs out and compare them to newer artists. So those kind of newer artists can compare them to longtime artists who have been around forever and have released a gazillion songs. And if you look at the number of unique words that somebody has used inside their first 35,000 words of song, you can see a very interesting distribution, okay? Down here, you'll find a lot of artists that are not known for their lyrical mastery, but yet some that are. Over here, you'll find essentially the gods of geek hip-hop. Aesop Rock, okay? Here's what I was looking for. Wu-Tang, MF Doom. MF Doom and Aesop Rock, I would say, are like, the top end of geeky hip-hop. And their huge vocabularies are much larger than most artists, and it is representative of what they are trying to do, that they are trying to cover both very complicated topics and that they're showing off in their lyrical ability in part through their vocabulary, right? It's super interesting to see how these are changing over time, right? So if you look at the 80s artists, they are here in the pink, and their average number of unique words is fairly close to the mean of all artists. But then something happened. In the 90s, there started to be a number of people that had a lot more individual unique words in what they were singing. And in the 2000s, even more so. And in the 2010s, what we're seeing is a pullback, and if in many ways, apparently, a trend towards very few unique words in these newer artists like Drake and so forth. Okay? So that's pretty interesting. It seems like a pattern, something which is reasonably robust, that we've pulled out of completely unstructured data. But in general, hip-hop, even with the modern pullback from unique words, still tends to have many more unique words than some other genres of music. In part, I'm sure, because hip-hop is actually a word-based kind of thing. Okay. Once again, Wu-Tang Clan definitely ain't nothing to F with, because Wu-Tang Clan as a collective of hip-hop artists has some very, very high ratings in their unique vocabulary usage. Okay? But I do want to highlight this again, right? This is a metric. It's a measurement. It isn't necessarily the truth. Because, for instance, where am I going with this? Here. This is Kendrick Lamar. And as you can see, he's dead in the middle of unique words used in lyrics. But many people will tell you that Kendrick Lamar is perhaps one of the greatest lyricists ever in hip-hop. And that he certainly covers complex, really, his songs are about things that other rappers tend not to get after, and he covers them in complex and really interesting ways, but apparently using a very average vocabulary. So you can contrast that to MF Doom, who's just showing off with the way in which he's constructing those songs. So complexity of the song is not necessarily encoded in this vocabulary. All right. Let me get back over here. Cool. All right. Recap. We just showed that it's possible to do things with highly unstructured text and to find interesting patterns. But I kind of ended it on this note here, right? Which is that, as I said earlier, measurements are not the thing they measure. So sometimes your measurement doesn't accurately capture the question you're after. Sometimes it accurately captures the question you're after, but it doesn't get at the nugget of the question you wanted to ask. Okay? Measurements are a stand-in for reality, and we have to be aware every time we use them that they are not the same thing as reality. And that leads to today's hot take. Data is not the new oil. It's not going to make us all everything and money and all that. Data is the new glitter. It lures humans in with its shininess. Wasn't that wonderful playing with those song lyrics? I thought so. It's so easy to get and to accumulate, right? It's found in places that you are least expecting it. Like, who knew that you could do so much with song lyrics until somebody showed you could, right? And we can find data about everything going on in our lives. It is almost impossible to get rid of. Your things that you generated are still going to be available and viewable to the rest of the world in 20 years. Your terrible mistakes on social media may show up and haunt you when you're 38, right? So everybody insists on using data without thinking through the consequences. Yep, that definitely falls into the category of some of the ethics stuff that we were discussing. So today's lesson was really about data and the ways in which we structure data. But I always want us to think about data in its good and bad, in its ethical impacts, and in the ways in which we think about the questions we can answer with it, even when we're talking about mundane topics like how we store data, right? So let's just bring it all home. What we really talked about today, the technical details, not the big kind of big picture questions. What we talked about was how we can store data, how data is used. We talked about different kinds of variables, right? Variables can be quantitative, like numbers, or they can be qualitative, like categories or just text or stuff like that, okay? When we store data, we can store them in either highly structured environments, like a SQL database, which enable us to do lots of very interesting operations on the data quickly and easily and maintain the data's integrity while we do that. They can be completely unstructured, like most of the internet. Or they can live in this middle zone, the semi-structured world. And this is usually where data scientists want things to be, right? We either want them to be in structured data sets, especially when we're operating on large amounts of data or data that a lot of people access. Or if we're working on more, it fits on a single computer data sets, and we're just doing an analysis locally, then we generally are going to operate in CSV or JSON or some other format like that, which puts structure into our data. Okay, so that is all I had for you today. I hope you have a lot of fun, and I'll talk with you at office hours or at next lecture. Bye.